Okay, we are back. Let's go for our next lab. This one's gonna be on evidence for dark matter right here, getting into really interesting topics. So dark matter is matter that does not interact significantly with light or ordinary matter, except through gravitational force. It is currently thought to make up the bulk of the matter of the universe. Why is this? Well, in fact, why do some astronomers even believe it exists? This lab investigates two phenomena that provide possible evidence for the existence of dark matter. Both the plots of galactic rotational curves, which display the orbital speed of disk material in the galaxy against its distance from the galactic center, and an effect known as gravitational lensing, provide strong evidence for the existence of dark matter. So there's two main evidences. One is gravitational lensing, and one is the orbital speed of matter in the galaxy as a function of their distance from the center of the Milky Way galaxy. You see? Okay. So math setup. Let's go to the first one. Universal gravitational constant. We've already done equations and calculations with the universal gravitational constant. Astronomers often use G in units of centimeter cubed gram per second squared as shown. Since we will be looking with mass units of solar masses, distance units in kiloparsecs, and velocities of kilometers per second, it will be convenient to express G in these units instead. So because we're looking at very heavy things, very fast things, they're going to be converting this units of G to other units. So in order to make the required conversion, you need to use the two conversion factors shown here. If you are rusty on unit conversions, review the lab that we did for lab 1 on unit conversions. So 6.673 times 10 to the minus 8 centimeter cubed per gram per second squared. In order to convert G from the previous units to units of kiloparsec times kilometer squared over mass of the sun times second squared. So you see how they're changing this? They're breaking this unit centimeter cubed, they're breaking it into 2 units of distance times each other. A unit kilometer squared. See, if this was cubed, you couldn't have this here. But they're breaking it into kilometers squared, and then they're multiplying it by another unit of distance to make the thing cubic, you see? And then the mass of the sun can be expressed as grams, so that's 1-to-1 relationship, and then second squared. So it says 1 kiloparsec is 3.086 times 10 to the 21 centimeters. One mass of sun is these many grams. Oh, okay. And so we will first convert units of mass from grams to solar masses. Okay. Using the conversion information given, we will fill in the blanks in the following equations by typing in the information needed to do the calculation. So converting mass, so you've got here G, let's say you wanted to convert this to, let's minimize this a bit. So you're just gonna press play here. So then you're just gonna press play. They're gonna put this units of the G, the regular units of G. First we write down the value and the units of the number we are going to convert. Then you go like that. Then you say mass of sun on the bottom, and then on the top you put grams. Then that's gonna cancel the grams here. You see? So likewise, we put the value for grams in the numerator. So that they're basically putting this in. Then that's gonna cancel that. Okay, so that one's pretty straightforward. And then that's gonna give you centimeter cubed, yeah, that's gonna give you centimeter cube per mass of sun. I think that's it for now. But then the next thing we need to do is break this up into kiloparsec and kilometers squared. So now use the animation above as a guide. Fill in the blanks here to complete the conversion. Remember, there are 3.086 times 10 to the 21 centimeters in a kiloparsec. So they're starting here by centimeter squared, centimeter squared. Oh, so they're taking this, let's see, 1.245 times 10 to the 26 centimeters squared per solar mass. Then they're saying multiply. Well, they just want you to practice essentially how to go from centimeters squared over mass of sun to this. They're gonna say to kiloparsec, and then centimeters squared to kilometers squared. I think they're missing. Oh, you know what? They're missing something here. They should be here centimeters squared. Yeah. So basically what they should be doing here is they should be taking this number, 1.327 e to the 6 centimeter cubed. But this number, they're having you practice on a different number. Instead of being 1.327, imagine this was 1.245 times e to 10 to the 26th. But now centimeter cubed, you can split it into two things. You can split it into centimeter squared. They're missing the squared here. And then times centimeter. You see? So you split it into centimeter squared times centimeter. Then here you say how many centimeters is a kiloparsec? Oh, that was in the previous page. Oh, no, here. It's giving it to us. 3.086 times 10 to the 21 centimeters. So you put that here, and then that's 1 kiloparsec. And then here, centimeters squared to kilometers squared. How many centimeters squared would it take to make 1 kilometer squared? So remember, the conversion is what? You got 100 centimeters is 1 meter, and then you got 1,000 meters is equal to 1 kilometer. So how many centimeters? So then you multiply 1,000 by 100. If 100 centimeters go into a meter and 1,000 meter go into a kilometer, then you got 100. You multiply these two numbers. 100,000 centimeters goes into a kilometer. Okay, so that's 100,000. 100,000 centimeters goes into a kilometer. But now if I'm going to square these, right? So how many centimeters squared is 1 kilometer squared? Well, that's going to be 5 zeros. Then if you square that, you get 10 zeros. So that's 10 to the 10th centimeter squared is 1 kilometer squared. So kind of tricky with the zeros. So that should be the conversion that we use. So then, let's see here. So then we should put here 10 to the 10th. 10 e to the power, 10 to the 10th. Yes, that's how to do it. 10 to the, or maybe, hold on. 1 times e to the power 10. Yeah, that's the way to put it. 10 to the 10th is 1 e to the 10th. Right? Because if I put 10 e to the 10th, it's going to make it e to the 11th. That's also tricky, right? How do you write 1 times 10 to the 10th? Well, you just write 1 e to the 10th. That should do it. And then that's going to be 1 kilometers. Okay, so then again, take a picture of that and your answer, and then show your work. Write it all out nicely and neatly, how you're converting from this to this answer. And then that way you're practicing how they do the conversion, how they get from here to the previous units, the kiloparsec times kilometer squared. And I think that's it for this section. Okay, then Milky Way's rotation curve. Okay, the rotation curve shows that velocity stays fairly constant, even at very large distances from the galactic centers. This observation implies the existence of extra non-visible matter that astronomers call dark matter. This figure is the velocity curve for our galaxy, the Milky Way. We immediately see that the curve does not appear to be decreasing as the radius increases. You see, the following equation gives the galactic mass m contained within a sphere of radius r. We can use this equation to determine the part of the Milky Way's mass that is included within any radius in the range of values shown on the plot. So this is the mass of the Milky Way as a function of the distance from the center of the Milky Way, and the velocity of, this is the velocity of the stars in the Milky Way as they're going around the Milky Way, divided by the constant of gravity. Of course, the constant of gravity we're going to use is going to be the one in the units of this one here. Let's keep that in mind. It's going to be the you know what? They never actually gave us the units of the 6.673. 6.673 times 10 to the minus 8. They converted that to, they showed us here how to convert it to, okay, is there any other play button here? No? Oh, okay, so let me actually calculate for this one and convert it to the units that they want. But because the practice one that they're giving, is slightly different than the one given here. You see 1.327, they're giving 1.265. So I'm gonna calculate it for this guy. So then how do we do it? We take that number, we go 1.327 multiplied by 10 to the power 26. Okay, then we say these many centimeters is 1 kiloparsec, so that means we divide it by this number. So we divide that number by 3.086, and divide it by 10 to the power 21. Okay, then we're gonna say divide that by 10 to the 10th. It's pretty easy conversion. So then remember, this is 100,000 centimeters is in 1 kilometer. Then if you square that, so divide that by 10 to the power 10th. Okay, so I'm getting now 1, 2, 3, 4, 5, 6. Oh, it's pretty. 1, 2, 3, 4, 5, 6. 4.3 times 10 to the minus 6. So the new value of the G is a very small number, 4.3, 1, 2, 3, 4, 5, 6, 4.3 times 10 to the minus 6. So that's going to be this value, 4.3 times 10 to the minus 6, right here. 4.3 times 10 to the minus 6. This is going to be the distance from the center of the Milky Way in kiloparsecs, right? And then the velocity is going to be in kilometers per second. Okay. And then what are the units of the G? Let's write this out. We need to see this so you see how the units work out. So then we have the equation is going to be mr v squared over g. So it is, the equation is m is equal to r v squared over g. So I calculated the g to be 4.3 times 10 to the minus 6, right? And then what units was that? It was kiloparsec. Parsec. I think they write it PC for short. Yeah, PC. Kiloparsec times kilometer squared per, I think it was centimeter squared. Yeah, exactly, centimeter squared. So how does that work? Well, if they give you the radius in kiloparsec and they give you the velocity, and I believe there's also here, what was the units of the G? I should have written it down from the beginning. The units of the G was, it's kiloparsec times kilometer squared over mass of sun second squared. There you go. Over mass of sun second squared. So this is over mass of sun second squared. So for example, if they told us that, imagine this is the Milky Way. This is the center of the Milky Way. And then this is the Milky Way right here. Imagine that a star here is going around the center of the Milky Way. Imagine this is our sun. We are about 2/3 of the way from the Milky Way center, our sun. So imagine someone were to give us the orbital velocity of the sun, and they were to say it's 250 kilometers per second. 250 kilometers per second. And the distance of the sun from the center of the Milky Way, I believe it's going to be around, what is it, 50, 60 million light years. So that's going to be, no, 56, 100,000. The Milky Way galaxy is about 100,000 light years across. I think this is going to be around 100,000 light years across. I think this is going to be around 30,000 light years. So I'm just guesstimating here. And then multiply that by 3.26. So that's going to be around 100,000 parsecs, a ballpark estimation of the location of the sun. So that's 100,000 parsecs. which in kiloparsecs is 100 kiloparsecs. I'm guesstimating that's where the sun is from the center of the Milky Way, 100 kiloparsecs. So then if I put the radius is 100 kiloparsecs, that's the R. The velocity is going to be, let's say it was given to be, where was that? Where did I write it? Did I erase it? I know I wrote it somewhere. Anyway, so let's say the velocity of the sun was 250 kilometers per second. Oh, I think I had written it here, then I erased it. Yeah. So then I'm going to square that, 250 kilometers per second. Then square that. And then divide that by G. But G is in this specialized units, 4.3 times 10 to the minus 6. So you guys can use the G that I got because I based it off of their numbers. You guys can use this G. Kiloparsec, kilometer squared over mass of sun, second squared. So then, wait a minute, did I use the mass of the sun when I did the conversion? Oh, okay, hold on. For the mass of the sun here, we don't have to convert. Okay, I did something wrong. Hold on. For this one, this number was already given to you in terms of the mass of the sun. In terms of the mass of the sun, and we didn't have to convert the mass of the sun. But this number is given in units of, hold on. Oh, this is already converted to mass of the sun. There you go. Okay. So this is already converted to mass of the sun. So there you go. That's fine. We could use the mass of the sun. We could use the number that I just calculated. Okay, got it. Perfect. Okay, so then how do the units work out here? So look at the units here. Kiloparsec times kilometer squared over mass of the sun times second squared. Well, the kiloparsec here from the G value, from the specialized G value, is going to cancel the kiloparsec here. And then kilometer squared is going to cancel this kilometer per second squared. This is going to cancel. And mass of the sun is going to go up. So that means that's already going to tell me how much mass is included in the Milky Way up to where the sun is. You see here? There you go. It's going to tell me all of the mass of all those galaxies, including the supermassive galaxy at the center of the black hole. You see? All the way up to the location of the sun. So let's see what we get. Do 100 times 250 squared, right? 100 times 250 squared. Hundred times 250 squared divided by 4.3 times 10 to the power negative 6. That's the G value. And this is my assumed speed of the sun, orbital speed of the sun, and then this is my assumed approximate value of where the sun is. Yeah, that's going to tell me that the mass of the Milky Way contained in the Milky Way is 1.4 trillion times the mass of the sun, up to the location of the sun. So what is the total mass of the Milky Way? Let's see. Milky Way mass. Mm-hmm. Again, we always refer to these side data. So here it is. It tells you the mass, the approximate mass of the Milky Way. So you see, we still don't know. It's anywhere from 0.8 to 1.4 times trillion. 10 to the 12 is a trillion times mass of the sun. This is the symbol for solar mass, one mass of the sun. You see? So it could be anywhere between 0.8 to 1.5 that the whole Milky Way contains. So what did I get? On my approximate calculation, I got where was that number I got? 1.45 trillion. So that's only the mass up to where the sun is. So I'm in the ballpark. And again, maybe I estimated the speed of the sun incorrectly and the distance to the sun, but you're kind of seeing that we are in the ballpark. That's how we are. That's how they're able to calculate the mass of the Milky Way, you see, and other galaxies like that from their rotational curves. Okay, so now you're seeing lots of good stuff there. Okay, so okay, now we go back to this. Wow, this is fun. Imagine calculating the mass of things that are just thousands of light years across. Okay, so then it says here rotational curve. In the equation, v is the rotational velocity of the galaxy at the distance r. This chart helps to calculate the value of the total galaxy mass m when the radius and the velocity of the galaxy are known. Enter the required values into the fields corresponding to different values of r. Press the total mass button to calculate the value of the total galaxy mass for the recorded data. Okay, so then it's giving you this chart. When I press now, it's probably should say nothing, you know. So you have to then go up here to the curve that they gave you, and you have to say, okay, they already filled out one of them for you. When the radius is 0.3, the velocity is 259. See, that's probably right this point right here. So what I'm gonna do is I'm gonna enlarge this, and maybe this one, maybe even take a picture of it. Take a screenshot of it. Go like this. So that I can then I can then make lines on it. Okay, so then it will appear on my desktop. Okay, then enlarge it. Okay, so what I could do is maybe tools, let's say annotate line. Okay, so you see the 0.3 Okay, so maybe I could make, this is the halfway mark between 0 and 20. Okay. Then I could copy it. So you see what, when they're saying radius is 0.3, that means it's all the way here. And then the velocity is 259. In other words, that's the fastest moving stars around the Milky Way. The fastest moving stars are moving at 259. So I was wrong to say that the speed of the sun was 250. You see, there it's more closer. The sun is probably somewhere here at about a 50 or 60, or maybe the sun. Yeah, even I was wrong with the distance. You see, so the sun is probably around 60 kiloparsecs, and its speed is more like 175 or 180. You see, so that kind of gives you the idea why my ballpark approximations were wrong. So the fastest moving stars are the ones right next to the black hole at the center of the Milky Way. You see, those are moving very fast. So you can see that this line is like goes up, up, up steeply. So the center of the Milky Way, the stars are not moving at all. Then as you go further away, they're moving faster, 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 faster. So it's kind of linearly going up steeply. So the supermassive black hole is governing what's happening at the center of the Milky Way, the speeds of the stars going around the supermassive black hole. But then the peak speed occurs at 0.3. Now they want to know what are the speeds of stars at each of these distances. Let's say 2 kiloparsecs. So the way to do that would just be, what I would do is probably take out of this 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe take 5 pictures of random ones and how you are getting the velocity of that, you see. So then you would say, okay, so what's the 2 kiloparsec? Where would 2 kiloparsecs be? So if this is 10, 2 kiloparsecs would be somewhere here probably. Yeah, 2 would be right about here. So that's probably pretty, so then I could make another one. Ah, nice. Oops. See right there? So that's about a speed of what? You're going to guesstimate right that points here. 150, 160, 170, 180, 190. Okay, so I'm going to say that's a speed of 190. Then I could take a snapshot of that and I could say that's 190. You see? Kilometers per second. Then, so when we fill that in, what is that going to give us? Then it's going to tell us here, so 190 kilometers per second. Okay. Then total mass, billions, visible mass, billions of mass sun. Okay, so then you're going to have total mass, billions of mass sun. So then you're going to put it into that equation, and you're going to calculate for how many billion solar masses that is. So basically put this data, 2 kiloparsec, velocity 190, into this equation. And then find out how many, this one is going to be in billions of solar mass. Okay. So this is telling us up to 0.3 kiloparsecs. They've already done the equation for you, and they've gotten 4.5 billion solar mass. That's how we know that the center of the galaxy, there must be a supermassive black hole. There's a lot of stars, and on top of that, there's a supermassive black hole. So already within the 0.3 kiloparsec, we got 4.5 billion solar masses. But of course, by now, we should be more. So this mass should be larger than 4.5. Okay? And then this is telling us the visible mass, billions of, so that means dark matter is the total mass divided by the visible mass. So that's weird. They've already done the calculation for the visible stars, the stars that we actually see. Okay. So then let's see here. If this is 4.7, this should be almost like a negative mass for dark matter. Negative 0.2. That's weird. Then over here, let's say we get something like that the total mass is, of course, it's going to be more than 4.5. It's probably going to be something like 6.2, let's just say, billion solar masses. Because when you go from 0.3 to 2, it shouldn't increase by that much. Okay, then you're going to do total mass minus 1.51. Then that's going to be 6.2. Let's just say for the sake of, let's just say 6.21 minus 1.51. That's going to give you what? 7. 5 minus 1 is 4. 4.7. That means already within 2 kiloparsecs, there's 4.7 billion mass of dark matter all floating around within the galaxy. If that's what this truly comes out. That's really weird, surprising. Okay, then let's say we go to the next one. Let's see, 190. So then how to do that? Well, we just go back to the picture. Then we go to 0.4, would be somewhere over here. Right? Because that's a half right there. So that'd be 0.4. And now right there, I'm going to go like this so I don't cover the 200. I'm going to go like that. You see there? So what's that? 205, maybe 207. It doesn't look quite 210. You see? So wherever the blue line is crossing the red line, and then wherever it's going over there, maybe 207. Okay, then based on that, I do my calculation. Okay, I do my calculation, and then I calculate what this is. So this is gonna, no, I calculate, sorry, I calculate, no, this one I calculate from the graph. So what did I say? 207. So basically for these two, you show work. For this one and this one. I don't know why the other ones they have is 0. So then you show work for that one. Let's see here. It should be more than 6.1. Let's say 8.14. Let's say. So you will show work for this one and have 2 shots so far. Or you don't necessarily have to take a snapshot for each of this. You could take one for every other one, like 1, 2, 3, 4, 5. Yeah. So take a snapshot for every other one. So then what will this be? Well, then it'll be 8.14 minus 31.3. Oh, that's weird. It's like a negative dark matter. Total minus visible billions of, okay. So that means that'll be 8.14. I'm just going to do it in my 8.14 minus 31.3, negative 23. Okay, then the next one, again, go to 6, put the line, determine where the velocity is. Now, one of the things you'll notice is that as you go farther and farther away, So let's say we go to this area. This is just a place marker to show where the 30 is, to make it easier. So as you notice that the velocities are like plateauing. They're not going down like they should, So by the time you're going here, they're just like, let's say if I go to, this would be 46 kiloparsec. This would be, this is 48 kiloparsec right here. 46, 44, and then 42. So let's say if I wanted to do exactly 50 kiloparsec, then it'll just be like that. Then what would that speed be? I'll go right there. Oops. Right there. That's the speed. You see? So you can kind of guess, okay, it's closer to 200. So guess a number there. You see? So then take a snapshot of that. And then you're going to put that equation again into here. Velocity, let's just say, you know what? Let me do like here. Let's see what we get. I'm going to guesstimate, let's say 172, let's say. I'm not quite sure why these fields are 0, because the mass should be increasing. Total mass, billions of solar mass. Billions of solar mass. This chart helps. So I have the total mass. Oh, it's doing the calculation. Oh, after that, after the second, oh, okay. So they don't want you to do too many calculations. After the first two, okay, so you could show work for these two, and then the other ones you don't have to show work for. The other ones, it's generating the numbers for you. So let's say you go 195, 183, and then so on and so on. And by the time you get there, it has plateaued. Let's just say 170. Okay, so the idea is that by the time you get to the total, oh, this is actually, total is 20 kiloparsecs. So they're actually not even going all the way up to, they're not even going up to all the way up to the 100 kiloparsec. They're just stopping right there at the 20. Already by the 20 kiloparsec, you've got 128.4 billion solar masses. That's incredible. And therefore, the mass of the dark matter is going to be that number minus 65.5. $62.9. Amazing. So as you're going higher, 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 you're saying, okay, that's the mass of dark matter that's contained in the Milky Way within a distance of 20 kiloparsec. So it's amazing that this thing is just like everywhere, so heavy. So just to give you an idea of why this is a dilemma, look at the orbital speeds of planets in our solar system. Notice how, as you go farther away, Orbital speed is essentially just a word for how fast an object goes around the sun. Okay, there's all these equations. Okay, so you see how the natural course of things, so imagine this sun is at the center and the planets are going around the sun. So based on Newton's law of gravity, the farther away objects are going to be going slower because they're farther away from the sun. So the natural order of things is that when you go farther away, the velocity should be decreasing. It's like this kind of, if you graph it, 47.9, Venus goes 35, Earth goes 29, Mars goes 24, Jupiter goes 13, Saturn goes 9, Uranus goes 6, and Neptune goes 5. So the orbital speeds are decreasing. Now assume that this wasn't the case. Imagine this was 47, and instead of this being 35, it was 42. Okay, imagine this, instead of being 29, it was 40. Imagine this, instead of being 24, it was 39. Imagine this, instead of being 13, it was 38. You see? So, and then this being 37, and then 36.9. See, so imagine it didn't drop as fast as it should, and then not only it didn't drop, but it eventually plateaued. That would mean there's sufficient dark matter in the Milky Way that fills all this vacuum space. And it causes the velocities of these objects to be much larger than they should. You see? That's sort of what's happening on the galactic scale over the Milky Way. That instead of the velocities of the stars dropping, they're not dropping as much, and then they're eventually plateauing. But in our solar system, there's no dark matter, you see? So dark matter is only over the galactic universal scales, but not inside of solar systems, you see? So that's a good thing that just to keep that in mind. Okay, so now we go back. I think that ends that. Okay, Milky Way rotation curve. This is an interactive plot of the dependence on rotational velocity of the galaxy versus the radius from the galaxy center. Click and drag the mouse on the plot area to get the coordinates of the point on the rotational curve. Okay, hold on. This is 0.3 G. Oh, there you go. G, they gave it to us here. 4.5 times 10 to the minus 6. Okay, cool. So they already are giving the G to us, and they're giving you this equation, and R is 0.3 and V 259. Okay, so what they're showing you is how to do the calculation, actually, just like I showed you. So if R is 0.3, so then this can actually do it doesn't go all the way to 0.3, huh? You know what, let's enlarge it. This might be the better way of doing what I was saying, right? So just because they already have the crosshairs. Oh, it's not going all the way to the, there's the linear function. You see how it linearly increases? It doesn't go to 0.3, but you can kind of see that it's close to, it actually looks like it's even bigger than 259. It says it says something like 274 there. Okay, so then for the other ones, let's see, we could use this. Let's say if one wanted to go to 2 parsecs and 4 parsecs and do that here. Let's see, could that work? 4 parsec, 2 works fine. 2, 198. Okay, then let's just use this. So then you can take a picture of this, 2, and then this one has more fine lines anyway. Yeah, so it beats the other method. So this graph pretty much should be the same as what they had here. Yeah, it's just more detailed. Yeah, might as well just use that. So 2, then you get here 4, then you can do all the way out to, oh, the only thing is that this can only go up to 20. Well, we only need to go up to 20 here anyway, so that's great. Nice, okay. So again, you could take pictures of that, 5 pictures for, you start at here, say 1, and then 2, and then 3, and then 4 and 5. Yep, there you go. Okay, electronic graph paper. So what is this one here? So the plot maker allows you to create an XY plot by manually placing points on a piece of electronic graph paper. So this is mass, billions of solar masses. This is selection of symbols. You may select the symbol to be used by clicking on one of the symbols on the right side in the box labeled symbols. Once you choose a symbol, move your mouse cursor in the grid, holding down the mouse button to enable the crosshair and cursor at the desired location. Release the mouse button and the symbol will be placed there. Switch into a new symbol. To switch to a new, click the button corresponding, okay. Clicking none, okay, there you go. Moving and deleting points. You may delete a point by control clicking on it. You may drag a point to a new position by holding the shift key, click and holding the mouse, and then releasing the mouse. Clearing, okay. Okay, so basically that one is going to be used for this exercise. So now let's open this here. So for this exercise, we'll be looking at the Milky Way rotation curve. Using the interactive rotation curve above, determine the velocity values for each of the R values given in the rotation curve chart above. So there's so many charts here. Mass of the Milky Way rotation curve examples. Your plot should look schematically like this one. Oh, okay. So they're saying that this is sample of what your plot should look like. Oh, okay. So then you got here Milky Way rotation curve examples. This is the mass. This is the total mass of the Milky Way. And this is the mass of visible matter of the Milky Way. And notice the gap between them is increasing. So most of the dark matter is located towards the outside of the Milky Way. You see that? So your final plot of the 3 mass distribution should look something like, you know what, by the way, let me just look at the location of the sun in the Milky Way, just so we have a reference. Of where the sun would be here. Location of sun in Milky Way. The sun is located nearly 27,000, so that's 27 kilo light years. So divide that number by 3.26. Remember, 3.26 light years is 1 parsec. So 27 divided by 3.26. Oh, the sun is 8 kiloparsecs away. Oh, there you go. 8 kiloparsecs. So that means the sun is around here. Right there, 8 kiloparsecs. That means within the radius of the sun, there's already quite a bit of dark matter. You see right there? So this is where our sun is. And inside the location of the sun, there's quite a bit of dark matter, but most of the dark matter is outside, right there. You see? That's why they only went up to 20 kiloparsecs in the analysis of this data. Because that's where majority of the stars are, you know. The rest of the outside of our Milky Way is all dark matter. You see, so this data over here goes all the way up to 100 kiloparsecs, but the sun is actually right there. It's 8 kiloparsecs right there. So the velocities are increasing up to where the sun is, you see, right there. So this is around where the sun is. So it's like it increases, drops, increases. You see, it shouldn't be, it should just be dropping like this, you see. If it was normal, it would just be dropping. So there's a bit of a spike here. That's probably because of dark matter right there. There's a bit of a spike. And then it drops, but then it doesn't drop as much. It plateaus. Very interesting. So that's kind of where the sun is. Okay, so then you're gonna go over here and you're gonna say, so your plot should look like this when you're done. They're just showing this as an example. So it says R is 0.3, 259. For this exercise, for each row in the rotational curve chart, record the value for velocity and then calculate the total mass for R is 2 and 4 using the relationship beneath the rotation curve. Okay. Well, you will have already done that. In other words, in order to do this, right, you've already done the 2 and the 4, the 6.21 and the 8.14, right? So that's basically, it says, just do that calculation and put that in there. So you're not doing any new calculation. So you just put, let's say, 6.21 and 8 point whatever it was. And of course, you're going to put the velocities that we recorded. And then let's say submit answer. Oh, I was wrong. So I mean, I didn't do it correctly, but make sure to, okay. So then it'll be something like that. So then you take a picture of that. So then question 2, now using the plot maker below, plot the data from your rotation curve chart. Remember radius in kiloparsecs, the first column in the chart is on the x-axis, the y-axis holds the total mass. The third column on the chart, the distribution of visible matter has already been plotted. Choose a symbol to display the value for total mass and click on the plot to place the symbols. Note the instruction tabs on the plot maker for help in plotting points. Now determine the dark matter column for your rotation curve by subtracting the visible mass, column 3, from the total mass. Record the first few values by completing the table below. So they want you to do it at R equals 0.3, 2, and 4. It would have been nicer to do it a little bit more, I feel like. Go all the way up to 8 or 10. But I guess they don't want to make you work too hard. So then you could say, okay, what symbol should we use? So then this is the visible mass. So then you go like this. What would be a nice symbol? Okay, let's see here. So then what would be at, what I would do is I would go over here and I would say, okay, at 0.3, the total mass is 4.5. Right? So where would that be on the graph? What are each of these? Oh, hold on. Okay, so this tells you the y value and this tells you the x value. Hold on. Mass in solar. Okay, there you go. So I want the 0.3 and 4.5. 4.5. Oh man, so 0.3. That one is hard to do. Yeah, why am I struggling? You guys are the ones who should do it. So, go down and then you take a snapshot of that. Go like that and take a snapshot, and then it should show the 0.3, 4.5. If you couldn't get it exact, that's fine. That's close enough. 0.3, 4.9. Okay, then the next one. Take this. No? Okay, so then the next one should be, hold on, what was the data? I'm gonna base it as if this is my data. 6.21. Oh, now it's the visible, the dark matter is below the visible matter. 6.21. Oh, wow, it's very hard getting it just right. I don't have steady hands. Okay, that's close enough. Take another picture. And then my last one is gonna be 4. And what was my 4? 8.14. Ah, okay, 8.14. Oh, that's 4. 8.14. And still below the visible matter. Wait, does that make sense? Hold on. 8.14. Oh yeah, it is a big negative. 6.21. Visible matter is 1.51. Visible matter at 2, the visible matter is 1.51. Oh no, they have a typo. The visible matter is not 1.51 at 2. It's actually more. It's 16.95. Or I mean, it's close to, based on their graph here, at 2, the visible matter is 16.38. At 4, the visible matter is 32.2. So let me look at that again. At 2, the visible matter is 16.5. I'm looking up here to see the visible, that's the y-axis. So at 2, the visible matter is 16.5. Something is wrong with this. It should be maybe 15.1. Yeah, 15.1. That means the visible matter is greater than the total mass of the Milky Way. So there's some negative mass that's unaccounted for. And then this is still negative, and then this is still negative. Oh, no, this one is larger. By 6, it should be larger. So by 6, they're telling us the total mass. Oh, but I just put in a number here, right? Oh, okay. So this wasn't something that I actually calculated. I'm not sure. So I don't know. This one is a bit iffy. These numbers that they're giving us, I think I trust that graph more. Is the 65.5 correct? Let's look. Yeah, that part's correct. She's around 66. It's around 65, 66. So that one's good. And then it goes down, the visible matter. It goes down. In other words, most of the matter that we see in the Milky Way that are visibly visible to our naked eye, to our telescopes, it's about 60 billion solar masses, or about 70 billion solar masses. That's the visible, and it's all visible up to about 10 kiloparsecs. So when we say that the sun is at 8 kiloparsecs, we're almost at the edge of our galaxy. Our galaxy is about 12 kiloparsecs in radius. Its radius is 12 kiloparsecs. So again, one of the things you're learning in this class is how to really look at data, how to analyze data, how to not get lost in all these numbers, and how to picture, visualize. This means up to about, because the mass is increasing, up to about, it starts to plateau at about 12 or 11. So that's the galaxy. Our sun is about 8, so that means it's almost near the edge of our galaxy. After that, most of the other material is just dark matter, and we don't see that. You see that? So here's what I want you to do. Take pictures of the 3 dots that you plotted that they require you to do right here, and then put in your answer here, and then just press answer. But on top of that, take all of these, take all of the ones that you've plotted here. Of course, you've calculated all, well, the thing will calculate it for you. So take all of these and plot all of them, and then way at the end, take a picture of your finished product. So way at the end. So basically show pictures for the 3, and then at the end, your finished product will look something like this. Hopefully it will look like this. First it'll be negative, then it'll spike, then it'll go something like this. I think it will look like this. See, by the time of the sun, where the sun is, the dark matter is already starting to appear. So, can I do copy paste? No. Well, I think if you just click, yeah, it creates more. So by the time that the sun, this is where the sun is right here. So that means there's a little bit of a gap right there, and already dark matter will start to appear. So by the time all of them are plotted, you're looking at something like this. You know, and then you say, oh my gosh, outside of 10 kiloparsecs, the galaxy is made only of dark matter. And then you take this final picture. Amazing diagram, just amazing, beautiful. And that'll be your final picture right there. Okay, I think that's it for that. So basically it will look like this when you're done. Okay, and Oh, now the next evidence for dark matter is gravitational lensing, which we have studied in the, was it the last lab? Yeah, from the dark black holes lab. Large masses can be bent the path of light as it passes nearby. This is an interaction called gravitational lensing. Einstein's theory of general relativity predicts that the presence of mass alters the structures of space-time. Okay, so we don't have to go too much into this because we've done this, right? That's a good thing about having done something, is you've already got the background knowledge. Gravitational lensing by a galaxy. Oh, I don't think we saw this picture before. Very large mass concentrations can, due to gravitational lensing, create two or more identical images of the same object. Observation of such identical images allow us to infer the presence of the lensing mass, even if it is not directly visible. So again, it comes back to gravitational lensing. A large enough mass can alter the path of light enough to produce dramatic lensing effects. The adjacent photo shows an example of two images of one galaxy produced by the lensing of another. Wow, you see that? So you're seeing almost, you're not seeing the arc thing, but you're seeing like four images, and then this is the lensing object, and then you're seeing four images of the galaxy that's in behind it. The Einstein cross, also known as QSO 2237 plus 0305, is made up of four images of the same quasar placed around the central dimmer galaxy. In fact, the observation of lensed images can indicate the presence of a large lensing mass, even if part or all of the mass cannot be observed directly. That means even if you don't see this lensing object, right? So this is us, the observer. This is the lens, and you might not even see it because it might be dark matter, you see? So in other words, you're looking at this source. So this picture actually might be, we don't see the dark matter here. So the central object you're seeing might actually be the galaxy that's farther away. You see? So you're actually seeing the source. And since this is dark, you're not seeing dark matter. You're just seeing the source itself. So imagine the light of the source is penetrating through the dark matter. And then you're seeing these lensed objects of the lensed images of that source, which is this cross. So imagine Einstein predicted that this would happen, and then they discovered it. So the left image is an idealized depiction of gravitational lensing for the case where the source and lens are not exactly aligned. We shall now use the angular separation of the two images from the lensing object and the redshifts and the source to determine the mass of the lensing object. Press the new case button to generate a new random case. First, we determine the angular positions, right ascension and declination of the lens, and two images so that we can determine the angle separating the images from the lens. Oh, so this is the lens. That means you're seeing here the lensing object. This is the image 2, image 1. And the lens is off to the side. So to use the left mouse button, or arrow keys on your clipboard to navigate cursor to image 1. Corresponding right ascension and declination will be displayed. Record these values on the main page. Okay, so use the left mouse button to navigate cursor to image 2. Finally, record the redshift values for the source and the lens below the table on the main page. Once you are happy with, okay, so then you just go like this. Oh, okay, the right ascension and the declination. That's its location in space. Right there. So 69.2862 degrees right ascension. Right ascension. And then the declination is how far above and below the celestial equator it is, right? So the RA measures how far to the right or left of the the word is escaping my mind now. But the RA basically is like latitude on Earth. It measures right, left degrees, and then declination is like, RA is like longitude on Earth. Just like it's measured from a line going through Greenwich, England. Declination is like latitude on Earth. It's measured from the celestial equator. So that means this image is above the celestial equator, 32.5 degrees. So you take a snapshot of that. Then you go over here, take a snapshot of that, the RA and the deck, and then this is the RA and the deck of the image 2. And then you already have their Z values. So we practiced this before, right? So it's good, again, that we've seen this before. Lensing simulator exercise. For a 2-image lens, the mass M of the lensing object is given by this. Well, it's just a complex formula, right? Exercise 3 and 4. You know what? This is too enlarged. Instructions. This animation describes the method of the calculation of the lens mass. Press the play button to get each next step of the animation. Press the back button to get a step. So let's say the RA, you know what, let's minimize it. So first we must determine the angular separation between the 2 images and the lens. Now that you have tabulated the right ascension and declinations of 2 images and the lens, we can estimate their angular separation by applying the Pythagorean theorem for a right triangle. Let us denote the right ascension by A and the declination by delta. So, they're using Greek letters. The right ascension is alpha and the declination is delta. And use a subscript 0 to denote the lens 1, the lens, 1 to denote the image 1, and 2 to denote the image 2. The angular distance between the lens and the image 2 is then, basically you're just taking the angular separation. So for example, let's say the RA of image 1 was 56.2. The declination was 31.4. The lens RA was 56.1. Of course, it's going to be more decimals, but I'm just doing it 1 decimal for now. 31.2. And image 2, 55.8. 30.4. And you're going to go they're showing you here actually with an example. So let us denote, okay, first they show you a random one with variables. Then they say, example, let the right ascension 69.23111, right ascension of object 2 is that. Then you're going to subtract delta 2 minus delta O, this minus this, and this minus this. So this is interesting because we're usually calculating distances on Earth. We're used to calculating like some object is some meters away from another. So this meter squared plus that meter squared is that meter squared. But in the sky, we calculate angular distances, right? So we say this is a certain degree above the celestial equator. This is a certain degree above the celestial equator. and then they're horizontally, they're different. So to calculate their angular distance, we do this squared plus that squared, and then square root of that. That's essentially what we're doing. Instead of taking distance, this separation, we're calculating angular separation. Very interesting technique, very interesting. Then we'll press play. Exercise. Use the table you populated. Calculate the separation in arc seconds of image 1 from the lens and enter below. Don't forget to convert from degrees to arc seconds. Once you have checked your answer, click play to proceed. Oh, okay. So then the other one has already been done. Oh, I think they did this. They already did this based on the numbers that I put. Ah, you see? In other words, they already calculated the separation in arc seconds from my image 2 to the lens. So you're always calculating the distance from here to here, and then from here to here. That's the thing. You're always comparing the image 1. In other words, you're comparing this guy, how far away this guy is from here, and how far this guy is away from here. So going back to this picture, you're comparing this to this, and then this to this. You see how off-center this is? Like that. So it's like this to this, and then here to here, like that. Okay, so then, and then the source redshift, I don't think that matters for this one. So then let's just say we put in a certain value. Let's see what will happen. Then you're gonna press OK. We now have theta 1 and theta 2, the lens mass equation. So we've got theta 1, theta 2, speed of light squared over 4g ds d1 over ds minus dl. It requires an addition the distances of the lens and the source from the observer. These are known from the above left diagram in terms of the redshift z1 for the lens and zs for the source. We may convert these redshifts to physical distances using the Hubble law. Use the redshift calculator to convert redshifts to physical distances. Okay, so what is their z distance? Let's just say, I'm just going to give not necessarily the numbers here, but let's say the z to the lens is, the source should be bigger, so 2.34, let's say, 1.22. Ah, okay. There's our trustworthy. That we had that before. So let's say the redshift was 1.22. Hubble constant. Whichever one you found that was using last time, I guess we could go with that, right? The Hubble constant 70 or 73, was it? Let's say 70, 1.22. Deceleration parameter, whichever one worked last time. If none of them worked, then go with the default of deceleration parameter 0. And then we calculate. And then we get this distance in parsecs. Right? So then there's a lot of stuff that goes into this. So, and you just put this here. Lens distance, you put in parsecs. Source distance, you put in parsecs. Theta 1, you put in parsecs. Theta 2, you put it in, in arc seconds. You put in arc seconds. And then the lens, you say calculate. And then it will give you the mass of that lensing object. Oh, here it tells you which Hubble constant to use. 65, and Q is 0.5, flat universe in the redshift. Use a Hubble constant 65 and Q is 0.5 for the flat universe in the redshift calculator to determine the physical distance to the lens and source from the redshift. Use that and the two angles previously determined to fill in the above fields, then click calculate to compute the lens mass. Okay, so let's see here. Lensing exercise. Follow the instructions of the lensing similar exercise above carefully to complete this exercise. Okay, so then here you're going to put the RA and the deck of all of them. Source redshift. That one is already given. So you put all of these, you put this, calculate the lens mass, then you put the lens mass, and then you press enter. So then how many pictures is that and how many calculations to show? So then you would probably have a picture for what? For the 3 for these, for the RAN deck, you would have, let's see, before this screen, let's go to the screen where, hold on. Okay, this is one screen where you could have another screenshot. So you put all your results in here. You put the source redshift, that's you're just getting that from the picture. Then you put your results in degrees, and then it will itself calculate this for you once you put these correct values, right? And then this one, you put it in. Then once you put it in, take a screenshot, okay? Then show the work for how you got that. Cool? If you're not getting a good answer, practice doing this one and see if you get the same answer as what they're giving you. You see? Because they've already done that. They will already do that for you. So then once you practice, then do this one and show how you're getting it. Put that in and take a picture. Then go over here. Go over here. Then go over here, put the Hubble constant that they want, the redshift Hubble constant that they want, and the deceleration parameters they want. Press calculate, take a picture of that. And then put the other Z, take one more picture. Then you go back here, so there's two more pictures here. Then you go back here, put in the lens distance in parsec, put in the source distance in parsec that this gave you, right, based on this number here in parsec, and then put in the arc seconds that you have from the previous picture. Then press calculate and show the lens mass. Press calculate and show the lens mass that they got. Then you also show the work for how to calculate the lens mass. So then go back to show how do you work. You have to use this. Speed of light squared, theta 1, theta 2 over 4g, ds, dl over ds minus dl. So how would that work? How will you be able to show the work? Well, c squared, theta 1, theta 2, so what will that be? So let's clear this. Let's write the equation down. What was the equation? The mass of this is the mass of the lensing object. Because now we've got two separate, it's a different formula that we're using. Because it's not an arc, right? We have two separate galaxies appearing on the two sides. So then we got here c squared theta 1, theta 2 over 4g c squared theta 1 theta 2 over 4g and then ds, distance of the source, distance of the lens, distance of the source minus distance of the lens over of distance of the source times distance of the lens. So that you're going to have now the speed of light is 3 times 10 to the 5th. Remember, we're going to want to have the speed in kilometers per second. Then you square that. The arc seconds, which you've calculated, so that's going to be, let's see, something like, let's say 2000, what was the one they had? As a sample, they had something like 3000 arc seconds. So then, based on the one that I had put, but it's probably not going to be that. So let's just say 2,100, just random, 2,172 arc seconds. And the other one is 1,900. I'm just making up a number, 78 arc seconds. And then over 4G. What was G? Remember, it was 4.3 times 10 to the minus 6. I think they said 4.5 times 10 to the minus 6. You could use either this 4.3 or the 4.5. And that was in units of what? Kilometer per second. Kilometer square times kiloparsec divided by mass of sun times second squared, right? Then the distance of the source, that's going to be in parsecs. I think the simulation will give it to you in, yeah, they're giving it to you in parsecs, like 10 to the 9th parsecs. Something like, they're giving you a number, something times 10 to the 9th parsec. So let's just say the source is 4.82 times 10 to the 9th parsec minus the lens is 2.73 times 10 to the 9th parsec. Oops. So I'm just showing you as an example so you can see how the math would work. Divided by 4.82 monstrous numbers, right? We're talking about times 2.73 times 10 to the 9th. So what that will be, the top will have units of parsec, but the bottom will have unit of parsec squared, because you're squaring 2 parsec squared. You see? Oh, there you go. Enlarge the whiteboard. So parsec or parsec squared. So what can we do here? Let's see. Parsec will cancel the parsec squared. So one of the parsecs is gone. This 10 to the 9th factors out, and this 10 to the 9th factors out and cancels with one of the 10 to the 9ths. Kilometer squared over second squared cancels kilometer squared per second squared. Right, and then we're left with parsec. Then change this to 1,000 parsecs. Oh, hold on, kiloparsec, kilometers per kiloparsec. In kilometers per second. Okay, how is the units going to work out here? Let's see. Okay, so let's see here. So what's left? We got the distance, the arc seconds, we got kilometers per second square, cancel this, kiloparsec. Times, oh, hold on. It's ds/dl over ds minus dl. Oh, there you go. The units weren't working out for some reason. Oh, I wrote this wrong. You see how a unit analysis helps everything? Everything is unit analysis. I wrote this wrong. It's ds/dl over distance of source minus distance of lens. There you go. You can catch errors. There you go. So therefore, it's just reciprocal of this. So you end up with this guy on top, this guy on top, this guy on top, and then you end up with a 10 to the 9th, an extra 10 to the 9th parsec on top. There you go. So 4.82, 2.73. I'm just going to write that on top. 4.82, 2.73. 4.82, 2.73. Times 10 to the 9th, an extra 10 to the 9th. Because remember, this was multiplied, so you get 10 to the 9th times 10 to the 9th, whereas this is just subtracted, so you just get a 10 to the 9th. So the 10 to the 9th on the bottom cancels one of the 10 to the 9ths on top. And then you get here 4.83 minus 2.73. And this is parsec. Then you can say 1,000 parsec is 1 kiloparsec. Parsec cancels. Okay, so then what I would do is the parsec will cancel, and the kiloparsec will cancel. So this will tell you how many solar mass this is. But now we probably have to do something with the arc seconds. So let me just calculate this, what that will come out. Let's put this all into the calculator. I'm going to take a picture of this. Okay, our trusty calculator here. 3 times 10 to the 5th. I'm going to square that to the power 2. So that's c squared times, let's say it was 2172 arc seconds, and it was 1968 arc seconds. Okay, divide that by 4, divide that by 4 times 4.3. That's the G value. Divide that by 4 times 4.3 times, okay, now all that, now all that times, what is that, 4.82 times 2.73, right, divided by 4.83 minus 2. or 4.82. Well, you know what? I wrote it wrong, I think. 4.82 minus 2.73. Close parentheses, close parentheses. You see how I'm doing that? So that I get all of the stuff correct. I'm multiplying that by opening a parentheses. I'm doing 4.82 times 2.73 divided by, but then now I have to make sure, put a new parentheses because the calculator should know that this is together. Okay? Equals, then I multiply that by an extra 10 to the 9th, and then I divide it by 1,000, right? Because I went from parsec to kiloparsec. So that's be 1.408 times 10 to the 29. And what would the units of that be? Well, it'd be arc second squared times mass of sun. So arc second squared times mass of sun. So here's my answer. 1.408 times 10 to the 29th. 1.408 times 10 to the 29th arc sec squared, because that's arc seconds, and this is the symbol for arc seconds, squared, or times mass of sun. So that means that mass of dark matter, the lensing object, in this case, the lensing object is a whole big, huge lump of dark matter, right? So it's that heavy, 1.408 times 10 to the 29 mass of the sun. But we need to convert arc seconds to something that is unitless. So the way to do that is to convert arc seconds back into radians to make it unitless, okay? Because the radian is actually unitless quantity, the radian. The radian is defined as like this. 180 radian, 180 degrees is pi radian. In other words, the radian is a unitless quantity, and the way that it's defined is that if a certain arc length of a circle is 1 meter, and the radius of that circle is also 1 meter, that circle subtends an angle of 1 radian. You see? But the radian itself is unitless because it's 1 meter over 1 meter. So meter over meter is unitless, you see? So for a degree of an angle not to have any quality to it, any quantity, it needs to be measured in a radian. So then here's how to convert. You can say 3,600 arc seconds is 1 degree of angle, but then square that. And then you can say 180 degrees is pi rads. And then square that. You guys are now officially math majors. Math is in everything. You can't study science or anything without math, even accounting, even economics or anything. So you take this number, you divide it by 3,600. So you see the arc seconds is going to cancel arc second squared. And 180 degrees is going to cancel with this. Then you're going to be left with radian squared, which is unitless. You see? So now you divide the number we got by 3,600 squared and also divide it by 180 degrees squared. So then we just go back to the calculator. Divide this by I'm going to put parentheses, 3,600 times 180, close the parentheses. Because I'm going to square both of them, we might as well just put them in the same parentheses and then square them. Okay, so that means the dark matter is that many times heavier than our sun. Right? We're always comparing things to our sun. 3.353 times 10 to the 17 times the mass of the sun. It's probably too heavy, I think, but you kind of get the idea that it's like, that's how to go about it. And then you should get the same answer then you should get the same answer that it gave you when you plug it all in, that it gave you here. You see, which is also the same answer that you will put here. Then you will press submit, and then you'll take a picture of that. So a lot of good stuff to show over there. I think we are done. Awesome stuff, man. Awesome. Dark matter and gravitational lensing comes together. And also the other previous part, the rotational curves of galaxies. You guys are now already full-fledged astrophysicists. So you should feel proud of yourself. Okay, thank you. Bye-bye.